Hi, my name's Blake, and today we'll be discussing the Drude Dispersion Model to model negative permittivity and permeability. This video is an advanced electromagnetics discussion, so if you are not familiar with advanced electromagnetics, I suggest you look at learning that material prior to continuing the video. Another assumption is that you are familiar and comfortable with manipulation of imaginary number components, as we will be using phasors and the imaginary number j many times in this video. So the Drude dispersion model can be used to model dispersion in a metal or other material. This model was developed in 1900 by Paul Drude, as in the name here. To begin the derivation, we will look at an electromagnetic wave, specifically the E field, and we will assume that it's polarized in the x direction. As this model is to describe metals, we can assume that in the metal there are immobile positive charges and mobile negative charges. And when the electric field is present, as the positive charges are immobile and the negative charges are mobile, the mobile negative charges will experience a force, and this force has two components: the typical force that we're familiar with, and the damping force. So we will call the familiar force the driving force, and the damping force F damping. Now the equation to model this electron dispersion looks like the mass times the displacement, second derivative of displacement with respect to time. This is equal to force, driving, as it is equal to m times a, where this is acceleration. And we will add the damping force as m times gamma, our damping coefficient, times the derivative of position with respect to time, as this is our velocity. And that will be equal to q E naught cosine omega t plus phi. Now when we assume time harmonic, we can write this equation in a more simpler form that we like, as m times our magnitude of position times the derivative of e to the j omega t over dt squared, plus the mass times the damping coefficient times our x naught phasor again, times the derivative of e to the j omega t over dt. And we also write this in phasor form as q E naught phasor times e to the j omega t. Now we know that e to the j omega t can be written or the derivative of e to the j omega t with respect to time is just j omega e to the j omega t. And if we want the second derivative, we can do the derivative of this term itself, which is equal to j omega squared e to the j omega t, and we can rewrite this term as negative omega squared e to the j omega t. Now, once we perform the evaluations on these equations to eliminate the derivatives, we come up with the equation m x naught phasor times negative omega squared times e to the j omega t plus m gamma x naught phasor times j omega e to the j omega t, and that's still equal to the right side of the equation that we haven't modified. Now, by looking at this equation, we see that e to the j omega t's can be cancelled as they're present on both sides, leaving us with m x naught phasor times negative omega squared plus m gamma x naught phasor times j omega, and that's equal to q e naught phasor. Rearranging this for x naught phasor, we find that x naught phasor is equal to negative q e naught phasor over m omega times omega minus gamma j gamma. Next, we consider a dipole moment, and the dipole moment is defined as q x naught phasor times some x direction, where this x direction can be arbitrary. Substituting this in, we find that the dipole moment for a single electron is negative q squared e naught phasor over m omega times omega minus j gamma. So this is our dipole moment for a single electron. Now, as this is a metal, we have two other equations to consider. First, that the electric field density D can be equal to epsilon naught, our free space permittivity, times our electric field plus our total dipole moment. Now, our total dipole moment varies from this dipole moment for a single electron, as this has to accommodate for all the electrons in the metal. So to accommodate that, we can write that the total dipole moment is equal to the factor n, the amount of electrons present, times our single dipole moment. Now, rearranging this equation, we'll call this 1. We can solve for the relative permittivity as D is equal to epsilon naught epsilon r e, which results in our total dipole moment being equal to epsilon naught times epsilon r minus 1, all times our electric field. Now, rearranging for epsilon r, we find that it's actually a function of omega, as our single dipole moment is a function of omega. And we find that this is equal to 1 minus nq squared over omega m epsilon naught times omega minus j gamma. Now, if we define a new term called the plasma frequency to eliminate these terms here, so we define the plasma frequency as nq squared over m epsilon naught. We find that the relative permittivity, still a function of omega, can be written as 1 minus omega p squared over omega times omega minus j gamma. Now, to continue, we want to eliminate this term as the way that it's written, as we prefer a real term and an imaginary term separated. So, to accommodate this, our relative permittivity, which can be written as complex. So, my complex notation will consider the bar underneath, can be written as the same as we have previous, but we multiply by the conjugate of this bottom on the top and the bottom. And this yields that the permittivity is equal to 1 minus our plasma frequency squared divided by omega times omega minus, over omega squared plus gamma squared minus j omega p squared over omega gamma 1 plus omega squared over gamma squared. Now we can see that this is our imaginary term, and this is our real term. Now, if we consider the case where there is no loss, i.e. our damping coefficient is equal to 0, we can find that the relative permittivity can be modeled as 1 minus our plasma frequency squared over our frequency squared. Now, this is the main equation that we're worried about, right here. And we can find that when omega p is greater than omega, we actually find that the relative permittivity is less than 0. Similarly, if omega p is greater than 0, or less than omega, we find that the relative permittivity is greater than 0, which this isn't really much of interest as we're pretty used to that at this point. Now, similarly, we can write mu r, our relative permeability, as a function of omega, and it is equal to 1 minus omega pm squared over omega m squared, where omega m can actually be shown that it's equal, so we technically don't need the m on this. Now, this follows the same conditions where if omega p of our magnetic is greater than our radial frequency, we find that mu r is less than 0. So these are the conditions that we're mainly considering with our model. Now if we consider a plot of epsilon and mu, where does this specifically fall? Now if epsilon is less than 0, but mu stays as we're used to it, it usually falls in this category. And vice versa, if mu is negative, but our permittivity is still positive, we fall in this area. The more interesting category is actually this area here, as this is the home for what we call metamaterials, which are materials that are not actually present in nature, but have been manufactured in such a way that we can create a permittivity and permeability that are negative. This corresponds with a motion or wave phenomenon that our propagation of power is one direction, we'll call it to the right in this case, but our propagation of the wave is actually in the other direction. Now this is the opposite of what we're typically used to in our normal scenarios where power and our wave travel in the same direction. Now going forward, I think we will step into the Fdtd simulator and we can go over what this phenomenon actually looks like inside a metamaterial. Okay, so jumping into the Fdtd that our professor Kenneth Chow provided from his 2017 class, we can see that most of the stuff was already set up for us. The only thing I actually modified was our plasma frequency, and something I didn't discuss is that the magnetic permittivity permeability, can also be modeled in a similar fashion. So what I did is the frequency that our simulator was set at is defined by our wavelength of our signal, and then omega is calculated. I modified the code so that the plasma frequencies was twice omega, so we would fall into the category of negative permittivity and permeability. The rest of this was just pretty standard. That you have your electric update, your absorbing condition, magnetic update, boundary condition for the magnetic field, and then all your plotting. So if we run this, and I drag it over here, we see that our electric field propagates to the right, as well as power and magnetic field. But the interesting part is when it actually hits this boundary. You can see that it starts going a lot different than you would expect. One thing to note is that there is no discontinuity, as there can't be a discontinuity across a boundary for electric field, magnetic field, or power. As the simulation may take a while, I will speed up the clip so that you don't have to wait this long, and we'll come back later. Okay, so now that the simulation is ran for a while, we can actually see that the wave is not actually affected when it leaves the material. i.e. the amplitude is the same and the phase or wavelength has stayed the same. What's more interesting is the fact that the propagation within the material is backwards, but the power transfer is still to the right. I think that's all for this video. Have a good rest of your day.